Thanks for nice words of introducing me. Just one minor correction. I have stopped working on isomorphism conjecture because I found progress too hard to do. So I switched to easier things. Okay, so this is a pretty simple talk of a function which has been around for quite a while. Let me just quickly go through the definitions and then we'll get to the main point. This is the Euler function. Leonhard Euler was a very prolific mathematician, and he made a number of contributions, including defining many functions. We are probably more familiar with the Euler's tangent function, which is very useful. But this one was also defined by Euler. It's an infinite product of 1 minus x to the k for k greater than 0. As one can clearly see, it's an infinite power series, and he studied some basic properties of this function. In fact, the reason of defining this function for him was to study partition numbers. And the way this function relates to partition numbers is very simple. If you represent by p sub m the number of partitions of number m, then 1 over ex is simply the generating function for partition numbers. Proof is straightforward. You just work out the details. So that was the reason for defining this function. And he then, to understand the properties of partition numbers, which was one of the key things in number theory, and it's something we still don't understand very well, he went on to study the properties of this function, and later on other mathematicians contributed to it. And it turned out that this function goes beyond, the contributions of this function went beyond merely defining partitions generating function, as we'll see very, very briefly. One interesting thing that came out of this is the following theorem called the Euler identity. And this identity expresses the Euler function as an infinite sum, as opposed to being an infinite product. That's how it is defined. And this has a very interesting form. If you notice, the coefficients are plus 1 or minus 1 only, and only for a few of powers of x. The rest of the coefficients are 0. And this identity has several proofs. One of the nicer ones I know is that you set up an involution between terms of same degree and opposite sign, and then that they just cancel each other, and very few of them, namely these ones, survive. In fact, this structure of the exponent 3m square minus m divided by 2, numbers of this kind are called pentagonal numbers, and they are intimately related to this Euler function. Okay, so that's what first came out of this study. Well, very soon this function was translated over complex plane, and that is, you assume that the x, okay, I think I missed something here. Yeah, okay. That is, x you assume to be a number, or a complex number, that is, and study what does this function look like. So this is an image shamelessly lifted from Wikipedia. It was defined by Linus Ipstas. And this tells us something about the values of this Euler function. This is a unit circle on the complex plane. It's undefined outside the unit circle. And along the unit circle, this takes a value 0. Inside the unit circle, it's always bounded. In fact, the maximum absolute value it takes is 4. And these colors represent the variation of the values of the Euler function, red representing 4, and as you go toward the other side of the spectrum, going from to blue and then to black, black represents 0. So that's the variation you can notice, and some very interesting structure seems clear. I mean, there's sort of a fractal structure which is inherent in this. As you can notice that, oops. This shape is occurring here and a smaller form here and all over the place. So there is a very nice fractal structure which has also been studied. In fact, there are a lot of symmetries inherent in this function. Some of those were captured by Derichlet, who defined eta function, which is a minor variation of the Euler function. Eta of z is e to the 2 pi I z. Instead of x, you write it as, substitute for x this term, and you multiply it for the sake of, let's say, normalizing the function by this quantity. And now this eta function, the symmetries become pretty apparent. For example, eta of z plus 1 is eta of z multiplied by this small quantity, the twist. More interestingly, eta of minus 1 over z is again a multiple of eta z, and what you multiply with is square root of minus I z. So these are two of the simple symmetries that one observes in this. There are many other symmetries. Of course, even proving this one is non-trivial. One has to do some complex analysis for getting this. And as let's say the number theory developed, there were certain functions called the modular functions that were defined. And the starting point of these modular functions, which again have a lot of symmetries, is the Euler function. Euler function led to the first modular function or modular form. I always confuse between the two. And then later on more such forms were identified. Okay, so that's the mathematical part of the Euler function, but this is a computer science talk. And especially I'm supposed to talk about computing the Euler function. This is an infinite power series. How do you even start thinking about computing it? So I'll come back to it in a moment. Before that, let me define another more familiar object called the permanent polynomial. This is simply permanent of a n cross n matrix, with the entries being variables xij's. This is defined in the usual way. And this particular polynomial or rather series of polynomials over varying values of n. This is supposed to be hard to compute. It was shown by Valiant to be hard to compute. And what I'm going to do in this talk is to relate the complexity of computing Euler function, which I am yet to define, to the complexity of computing permanent polynomial. Okay. So now let's talk about how does one compute the Euler function. And this fairly obvious way, in fact there are two obvious ways of computing it. Take this infinite power series and chop it off at various powers. And so each one of these truncations gives us a polynomial. So we get a family of polynomials. And we would like to design circuits to compute this family of polynomials. And two natural ways of truncating is, one is to take this infinite sum representation of Euler function and cut it off at certain degree. The other is to start with the original definition of take the infinite product representation and chop it off at certain degree. And we'll consider both of them. So let E sub sigma represent the sum truncation and E sub pi represent the product truncation. Now, in either case, the Euler function is obtained by taking a limit as n tends to infinity of both of this. And E sub sigma is a polynomial of degree order n square, and so is E sub pi. And we can naturally assume that a circuit family computing any of these two family of polynomials as computing the Euler function. So it's giving a better and better approximation to the Euler function as we increase n. And since it's a polynomial, it's natural to think of an arithmetic circuit computing these polynomials. So that's what we'll restrict our attention to. Okay, so what are arithmetic circuits? Again, I am sure everybody is familiar with it, but let me quickly go through this part also. An arithmetic circuit computes a polynomial in one or multiple variables over some underlying field x. Here I am just defining it in terms of computing a polynomial of a single variable. So the input to the circuit is just a variable and some constant -1, and then it uses addition and multiplication operations to compute the resulting or the final polynomial. The size of the circuit is defined to be the number of, typically or more often it's defined as number of gates. For some reason which I don't quite understand at this point, I've defined it as number of wires, but these are nearly identical notions, so it doesn't matter about how you take it to be. Okay, so that's an arithmetic circuit, and clearly it can compute any of these two family of Euler polynomials that I've defined. In fact, it's easy to see that a depth 2 arithmetic circuit, which is a sum of products of size order n square, can compute any of these two families, for the simple reason that these are E sub sigma or E sub pi limited to n are polynomials of degree order n square. So it's a big sum of order n square terms. Can we do better? Well, at least for the E sub pi we can use a depth 3 arithmetic circuit, which is a product of sum of products, to compute E sub pi using only order n size. And that's because E sub pi is defined as a product of 1 minus x to the k for k going from 1 to n. So you have a product at the top which is of fan in n, and in the middle you have this summations or subtractions of fan in 2, and at the bottom again you have a product which computes various powers of x. So order n size in total. So the natural question then is, can we increase the degree and reduce the size further? Well, at least for some polynomials we can certainly achieve this. I mean, this is a very simple example which shows that this polynomial, which is simply 1 plus x square plus up to x to the n minus 1 actually, we can compute this polynomial by a depth 3 circuit of order log n only, by simply taking this log n size product. So in the similar way, can we define some clever way of computing these Euler polynomials as well? But that's not clear. Of course, this is not something that has been very deeply investigated. So this being not clear does not necessarily mean that we cannot do it. But no simple trick is known which allows us to compute either of the two families of polynomials in a more efficient way. In fact, it's more interesting, it will be more interesting if we cannot compute them in a substantially better way, as I'll show you now. So I'll prove two theorems, both reasonably simple. The first one is regarding the computing the family E sub pi, the sum family. And this is stated in reasonable generality, but just take S for the sake of understanding to be the identity map. That is, S of x is x. So if suppose every circuit family computing E sub pi requires n to the omega 1 time. So I'm stating it assuming S to be 1. N to the omega 1 size. Then the permanent polynomial family requires arithmetic circuit of exponential size. And this happens over any underlying field f. So a lower bound on the complexity of the Euler polynomial in the sum form gives us a lower bound on the complexity of the permanent polynomial. Second theorem, the corresponding but slightly weaker theorem for the product polynomial. And this is more interesting also, as I'll argue later on. So this is a fairly hairy expression. So if suppose every circuit family computing the product polynomials over some field f of characteristic more than 2 has this strange complex looking quantity as its size. Now here you can't assume S to be identity, or can I? It won't make sense. Yeah. So let's see if I can give you a feel of this. Okay, so let's say S is identity. I think I can take S to be identity. This becomes 2 to the omega poly n, 2 to the poly n. Not poly n here, actually typically one should take this constant here to be something much smaller than 1. So suppose we cannot compute this product family in size 2 to the n to the epsilon. Then the permanent polynomial requires exponential size arithmetic circuit to compute. So this is weaker result than this, but it is still interesting to know. In fact, a more interesting thing perhaps would be that choose S so that this becomes super polynomial. And then this would also be super polynomial. So a super polynomial lower bound on the size of circuit family computing E sub pi gives us a super polynomial lower bound on the permanent polynomial. Something similar was recently shown by Pascal Coiron.
You said before that there was a polynomial upper bound.
Sorry, I shouldn't say. No, that's very right. I should have been more careful here. This is super polylog. Super polylog lower bound. A super polylog lower bound here gives a super polynomial lower bound here. That's right. Okay, so Pascal Coiron showed a theorem somewhat similar but slightly weaker than what this theorem states. Okay, so let's go through the proof of these two theorems. As I said, they are both pretty simple. The first one is simpler, actually. So let's start with the sum polynomial. It's E sub pi n is this degree 3n square plus n over 2 polynomial. The coefficients of this C sub t are 0, plus 1 or minus 1, as was observed by Euler. Now what we do is we convert this univariate polynomial into a multivariate polynomial, and that's a fairly standard trick one uses. Take the degree, maximum degree of this, which is 3n square plus n over 2. Take the log of that, which I'm defining to be the number u, and take that many distinct variables. So here z1 to zu, and define the polynomial m sub n over these z variables to be this, whose coefficients remain the same. The difference is that instead of x to the t here, we have the product of zj's. And the way to think of this is to view z2, for example, as representing x square, z3 as representing x to the 4, so successively higher powers of x, and just multiplying these corresponding zj's gives me x to the t. So you take the binary representation of t, take the ones and take the corresponding zj's and multiply them here. So that's the multilinear version of this univariate polynomial. Okay, so we get a multilinear polynomial for this, and the number of variables here are order log n. Now notice the coefficient of this multilinear polynomial, which is c sub t, is computable in polynomial time given t. Now t is a order log n bit number. So when I say polynomial time here, I mean polylog n time. And the reason is very simple, because the c sub t's have very nice structure. C sub t's are 0 whenever t is not of this form, and whenever t is of this form, depending on the sign here, c sub t is +1 or -1. And this is a very easy problem to solve. So in polynomial time given t, we can easily figure out whether there exists an m of this kind or not. Do a binary search, for example. Okay. So now we have this multilinear polynomial where the coefficients of this are efficiently computable. And now you simply use the variance hardness result of permanent to show that we can compute this polynomial over order log n variables as a permanent of a order log n sized matrix. And the entries of this matrix are either constants from the field or the variables z1 to zu. For technical reasons, we need to actually multiply this with the power of 2, and that's why we can't work with characteristic 2 here. But for any other characteristic, this is fine. Okay. Now, suppose permanent family can be computed by sub-exponential size. I'm ignoring the s here and taking s to be identity. Sub-exponential size circuits. Then this, correspondingly, this family can also be computed by n to the small o of 1 size circuits. Is that clear? Because here there is an exponential drop in the size here. The matrix that we get, whose permanent is this polynomial, has size order log n. So if permanent family, a permanent of an n by n matrix requires sub-exponential size to compute, then this permanent of order log n size matrix will require n to the small o of 1 size to compute. And so let's take the circuit which is computing this polynomial, and then this is a multilinear polynomial. Replace the variable zj by suitable power of x to the 2 to the j. And this is a translation that transforms m sub n to the polynomial e sub sigma. And this translation requires replacing input by certain powers of x. But computing these powers itself doesn't take too much additional time, because this x to the 2 to the j can be computed with j multiplications. So that adds only order log n additional gates. And then since the characteristic of field is more than 2, you can multiply by inverse of 2 to the minus c log n to the circuit to get the resulting circuit computing the polynomial e sub pi of x. It's a univariate polynomial. And the size is n to the small o of 1, which is a contradiction. So this shows that if we have a lower bound, let's say even like n to the epsilon on the circuits computing e sub sigma, then we get an exponential lower bound on circuit computing the permanents. On the other hand, if we choose s to be such that we get a super polylogarithmic lower bound here for circuits computing e sub sigma, then we get a super polynomial lower bound for circuits computing permanent. So that's the first theorem. Now let's come to the second one. If you recall, this was about the product polynomial. So let's assume, in fact, let's go back quickly to the theorem. So this is, as I said, a weaker theorem in terms of the size here, and also the lower bound it shows for permanent polynomial is not over the same field f, but over the integers. So that's also something we must keep in mind. Okay. So for the sake of contradiction, let's assume that there is a circuit family of size 2 to the small o of n, computing s of 2 to the small o of n now, because I can't ignore s here, computing the permanent polynomial over integers. Okay. And let p of x, this is the same polynomial e sub pi for n variables. It's a univariate polynomial of degree half of n times n plus 1. And suppose the characteristic of the field f is small p, and since coefficients of the polynomial capital P are in f sub p, so we might as well assume that the underlying field is the prime field, which is f sub p. Extend this field f so that the size of extension f hat is at least n square and not substantially more than this. So let the size be q. Now I'll come up with an very standard alternative expression of p using Lagrange's interpolation formula over the field f hat, and I can write p sub x as sigma or sum over alphas in f hat, p of alpha times this expression, which is just comes out of the Lagrange's formula. Now notice a few things here, which is which allows us to compute this efficiently. Number one, the product of alpha minus betas, this here, beta not equal to alpha, is simply minus 1, because beta runs over all elements of f hat except alpha. Second, product of beta in f hat, beta not equal to alpha of x minus beta, which is the term sitting here, is this obviously, and this is simply x to the q minus x, and therefore this product is this sum. So this allows us to express the polynomial p as a big sum. Remember, originally the way it was defined was a brick product. So p of x is this sum, which I can rewrite it as this sum, and now the coefficients of various powers of x here are of this form: sum over alpha in f hat, p of alpha times 8 alpha to the j minus 1. So now what's clear is, if I can compute this p of alpha efficiently, then I can compute this big sum as permanent of a small size matrix, and therefore I can compute this big sum also as a permanent of a small size matrix. So the key thing that needs to be done now is to somehow find an efficient way of computing p of alpha. Now p of alpha is this product, 1 minus alpha to the m going from 1 to n. So I cannot hope to do it directly in polynomial time. Now again, notice that the polynomial time, when I say here, the amount of time I have available is log n to the constant, because everything is scaled down to order log n level. Whereas there is a product of n terms, so there is no way in polylog n time I can hope to compute this directly. So one has to use some indirect way of doing it. Well, instead what I cannot compute it direct in polylog n time, but what I'll show is that one can compute it in p to the sharp p. And it's pretty straightforward. Fix a generator G of f hat star and define a non-deterministic Turing machine N, which on input alpha, which is an element of f hat, guesses T and M with T between 0 and Q and M between 1 and N, and checks if G to the T equals 1 minus alpha to the M. And if yes, it outputs T on that. Oh, this should be path, not the part. So it has this multiple guess paths, one for each T and M. If it gets this equation right on that path, it outputs the value T on that path. Otherwise, it outputs a value 0 on that path. Now, it's clear that the number, if you look at this non-deterministic Turing machine as computing a sharp P function, then the function that you get compute here is this sum, M going from 1 to N of T sub M, where G to the T sub M is 1 minus alpha to the M. And therefore, P of alpha is G to the sharp N of alpha. So G to the exponent, this exponent, which is the number computed by this non-deterministic Turing machine, gives me P of alpha. And therefore, I can compute P of alpha in P to the sharp P. This is a sharp P computation, and then raising it to the G, a certain power of G, is a polynomial time computation. Okay. Now let's use the fact that permanent is complete for sharp P, and our assumption that permanent over integers can be computed by circuits of small size. But now this is our permanent computation over integers, because I need to compute this number, sharp N alpha. This is to be done over integers, or at least modulo the Q minus 1. So I can compute P of alpha as a small size Boolean circuit through a small size Boolean circuit, because it's computable in P to the sharp P, and sharp P we can do it with small size circuits. And now so each coefficient of this polynomial P can be computed by a small size circuit, and then just applying the hardness of permanent once again over this, for this polynomial, which is a big sum, exponential size sum, where each coefficient can be computed by a small size circuit. Apply the hardness of permanent once again on this, we get that the polynomial P itself can be computed by a circuit of this size. So you apply this S twice, and that's why you get this hairy looking expression. And this contradicts the hardness of computing P. So as I said, if you assume this to be super polylog, you get super polynomial. Oh, wait a minute. If you assume this to be polynomial, you get polylog here. And so if there is a super polylog lower bound on hardness on the computing the Euler product polynomial, we get super polynomial lower bound on permanent. So for this reason, we might want to, or will be happier if one can find a lower bound or good lower bound on the hardness of computing the Euler function. But this is not the end of story. We can get something more out of it if we can prove a stronger result than just this lower bound. And that more is a black box de-randomization of identity testing problem. So let me quickly define the identity testing problem, again something which should be familiar to everyone. Given an arithmetic circuit over some underlying field f, we want to find out if the polynomial computed by this circuit is identically 0. And there is a number of randomized polynomial time algorithms known for it. No deterministic one is known. And this is also interestingly connected with the Euler function. Now let me describe this connection. So now I'm considering polynomials that contain the Euler function in the sense that one of the factors of these polynomials is the e sub pi n for some value of n. Or in other words, the let's say P sub m is a family of polynomials with P sub m of degree polynomial m, and we say that this is a n multiple of the e sub pi family if for every m e sub pi of n x divides P sub m. That is, P sub m contains as one of the factors 1 minus x times 1 minus x squared times 1 minus x cubed up to 1 minus x to the n. And then it has some other products. So we can construct a number of such families, of course. So we start with e sub pi n and just multiply it with arbitrary polynomials. The question that one asks now is, after taking e sub pi n, suppose it's computing e sub pi n is hard, can I multiply it with another polynomial so that the resulting polynomial becomes easier to compute? And by easier I mean whatever is the circuit size required to compute e sub pi n, we can compute it with even smaller size circuit. Can this happen? A simple guess would be no. That is, if I require circuits of say polynomial or n to the epsilon size to compute e sub pi n, then I should also require circuits of same n to the epsilon size or thereabouts to compute every n multiple of e sub pi. And if that is the case, then we get a black box de-randomization of identity testing. Again, pretty simple. And this is the theorem stating this same thing. And the proof is also very straightforward. That assume that every n multiple of e sub pi n requires circuits of size n to the delta. And take an arithmetic circuit. This is the circuit for which I need to test identity testing. It's a circuit of size m, computing a polynomial over these m variables. Let's call it q over some underlying field f. The degree of q by its size is bounded by 2 to the m. And now let's give a black box de-randomization of this, checking if this polynomial is identically 0 or not. So the algorithm is as follows. Capital D is 2 to the m plus 1, and this is a standard trick of translating multivariate polynomial into univariate. This should be y sub I, not y to the I. Replace y sub I by x to the capital D to the I minus 1 as inputs to C. What this ensures is this substitution ensures that the resulting polynomial is non-zero if and only if the polynomial q is non-zero, for the simple reason that we are mapping different monomials to different powers of x. And the additional size required is order m square wires to this. And so let's say Rx is the resulting polynomial, univariate polynomial that we get. And it's easy to see that Rx is non-zero if and only if the original polynomial q is non-zero. Now test if this polynomial R is 0 modulo x to the L minus 1 to the k for various values of L and k. Well, L varies from 1 to n, and n is defined to be m to the 3 by delta. So it's a polynomial in m. And k is the largest number such that x to the L minus 1 to the k divides e sub pi n. So k is clearly not going to be very large. And output 0 if and only if all tests succeed. That is, if all Rx is 0 modulo all of these, then we conclude that R is 0. And why does this work? Well, first of all, it's a deterministic polynomial time black box algorithm. doesn't look at how the circuit C works. And if all the tests work, that is Rx is 0 modulo each one of these, and this L goes from 1 to n, this clearly means that E sub pi n divides the polynomial R. Well, if E sub pi n divides the polynomial R and R is non-zero, then R is an n multiple of E sub pi n, and by assumption, R must require a circuit of size n to the delta, which is m cube, to compute. But the circuit C hat, with the one that we started with, modifying the circuit C, is of size only order m square. And that's a contradiction. So that's three very simple theorems I have shown you. Let me end up with some open questions. This is somewhat annoying that we had this very complicated looking expression involving two S's in the second theorem regarding E sub pi n. We can get rid of that if we can show that the coefficients, or rather P alphas, that we were trying to compute, instead of being computable in P to the sharp P, if we can somehow show them to be computable in mod P. It's mod P sub P. And if we can do that, then we can get rid of that additional S. Can we prove a lower bound on E sub pi n? Well, that's pretty obvious. Next question. And even stronger, does every n multiple of E sub pi n require circuits of size n to the n to the epsilon? This will, of course, this is the strongest result that one can get. And with this, one will get the black box de-randomization of identity testing. Finally, a conjecture. As you would expect, answer to all three questions is yes. And if the conjecture is true, we get everything that you can ever hope for. Exponential lower bound on complexity of permanent, a complete black box de-randomization of identity testing. And this conjecture relates, if you think about it, the size of an arithmetic circuit computing some polynomial to the number of distinct small roots of unities that polynomial can have. And it's fairly similar in spirit to the tau conjecture of Schopf-Smale that relates the size of an arithmetic circuit computing a polynomial to the number of distinct integer roots the polynomial can have. So instead of integer, now we are saying distinct small roots of unity that can be there. And the conjecture says that if the size is small, the number of distinct small roots of unities are also small. That's it. Thank you.